Hey everyone, I think we're live. Perfect. Thanks everyone for coming. Today we'll talk about a bunch of stuff, of course. The first will be we'll talk about databases today, just a little bit in terms of state workloads and how stateful workloads and how we can run. I'll show you how to run MongoDB as a stateful set inside Kubernetes. This will also involve talking about um, persistent volumes, persistent volume claims, and then I'll show you how to run the MongoDB as a stateful set in the cluster. Then after that, we'll talk about security a little bit, things like service accounts, role-based access control or RBAC, and network policies. And then we'll close it out with CRDs and custom resource definitions. I'll show you how you can create your own resource and how you can create your own controller for that resource to add some more logic or smarts to it. All right, let's get started. So running, I mentioned this before, that running stateful workloads inside Kubernetes is a little bit different than when we're just running a stateless services, right? The reason is that containers and pods, they can get created and destroyed at any time. Cluster nodes can go down, they can be added or removed, which can then cause in turn the pods to be rescheduled on different nodes. So if we want to run a stateful workload, something like a database, in the same way that we're running a stateless service, all of our data would be lost the first time the pod is restarted or the pod is rescheduled. Now, for that reason, what we need to do is we need to find a way how we can store the data outside of the containers so the data does not get removed when the container is restarted. So the way we do that is we use this abstraction called volumes. And last time when we talked about config maps and secrets, we've already used volumes. We haven't talked about them explicitly then, but we already used them. So the volumes live as long as the pod lives. So if the container within the pod gets restarted, the data will be preserved. However, once you delete your pod, that volume is gone as well. It will be deleted. Now the volume itself is, it's just a folder that may or may not have any data in it. And then it is accessible to all the containers within that same pod. Now how that folder gets created and what's the medium that's backing it, what's behind it, that's determined by the volume type. So let's look at a couple of volume types. There's way more than what I'm listing here. These are just a couple of them so you get an idea on what they are and how this works. The most simple one is the empty directory one, and this one gets created when a pod gets assigned to a node in your cluster, and then it will exist as long as the pod is running. As the name suggests, the volume is initially empty, so there's nothing in there, and then the containers in your pod can then write and read files from that volume. Once the pod is removed, the volume will be deleted as well, so the data will be gone as well. Then the next one is AWS, Elastic Block Store, Azure Disk or File, GC, Persistent Disk. So these are fairly similar. The difference here is that the contents of these persistent disks are actually preserved. So if you're using GC persistent disk, what you can do is, so that volume type allows you to mount a GCE persistent disks into your pods, which also means that you could pre-populate that disk with any data that you like, and then that data will be available to your containers and it'll be preserved. It'll be preserved between the pod restarts. Now, each one of these AWS, Azure, and GCE volume types, I think the requirement for each one of these is that your pods are running on the VMs in that cloud. So you cannot use, I don't think you can use a GC persistent disk if you're running an AWS and then vice versa. There's also the host path where you can mount a file or directory from the host node's file system. So if your pod is running on node 2, you can use the host path to map a specific folder from that specific node. This host path is probably, if you've used Minikube before, then you've probably used host path. And then there's the last one in the list. It's called the persistent volume claim. And this volume is used to mount a persistent volume into a pod. So persistent volumes are just a way for users to claim any durable storage. So durable storage in this case would be GC persistent disk or block storage on AWS or Azure disk. So there's a way for a user to claim some type of storage like that without necessarily knowing any details about the cloud environment. So think about it. I just want to get some storage. I don't care. I don't care where it is. I don't care what it is. Maybe I care the size of it and the speed of it, but just give me. I don't want to configure it myself. Just give me the storage. I just want to use it. There are two parts when you're using the volumes. The first one is where you define the volume. This is lines 11, 12, and 13. And you define the volumes in the pod spec. So this is not defined per container. It's defined per pod. You give a volume a name. In this case, we named it pod storage. And then you specify the type. We have the empty dir here. But if you're using if you're using a different volume type, you will have different settings and different configuration there. So once you have the volume defined in your pod, then you need a way to use it somehow. And this is where the second part comes in, where you actually say, I want to mount that volume that I defined in the pod. I want to mount it in my container. The way you do that is on line 8 with the field called volume mounts. And then you can specify the name of the volume that you want to mount. And you can also specify a path where you want that volume to live and be accessible from within your containers. Also, there's no limits, I guess. You can have more than one volume and more than one volume mounts. It doesn't have to be just one. And not all containers have to mount the volumes either, right? So you can have the volumes defined, but you don't have to necessarily mount them. So let's talk about the persistent volumes and persistent volume claims. So as I said, this is just another volume type you can use to mount a persistent volume into a pod. So persistent volumes are just like regular volumes, but their life cycle is independent of any individual pods that use them. So meaning if the pod gets deleted, the persistent volume will actually continue to exist. So using a persistent volume and a persistent volume claim, you can claim a portion of some storage. So you can claim a portion of a persistent disk without knowing about the details on how that storage was provisioned. The volume claim, that's the configuration on what type of a volume do you want. In that volume claim resource, you can specify the requirements for your storage. So these are the things where you can say, I want some fast storage. I want it to be 10 gigabytes, or I don't care if it's fast. I want just whatever is the default. Give me that one, or give me a slow one and a small one, whatever. You can configure those requirements when you're requesting the volume, when you're claiming the volume. Now, if you think about this as a user, right, you just want to get a piece of storage, right? You don't care where the data is necessarily stored or the specific configuration for it. There are two ways that you can create persistent volumes. So one way is that this is usually pre-provisioned by cluster administrators. So depending on where your clusters are running, the administrators can create different storage classes, or they can create different persistent volumes, provision them for you to use. The second way is where you can create a resource called a storage class, and then you can create persistent volumes dynamically based on that storage class. So once the persistent volume is created, this can either be pre-provisioned or dynamically using the storage class. Then you need a way to request it or to claim it, and this is what the persistent volume claim does. It's a resource that claims a specific volume. So inside that, you can, as I said, specify the size and different access modes, right? So when you create a persistent volume claim, what a Kubernetes controller will try to do, it'll try to match that persistent volume claim with a requested persistent volume and then bind them together. Now, in case that the matching volume does not exist, your claim will remain unbound. So if you only have 2 gigabyte volume, persistent volume created, but you request like 200 or something, that claim will remain unbound because there's no volume that's going to match your claim. However, as soon as that persistent volume either gets created or becomes available, the persistent volume claim will get bound to it. So here's whatever I just talked about, but in a graphical way. So you have an admin that can provision these persistent volumes for you, or you have the storage classes, which I'll talk about next. And then you have a user who uses the resource called persistent volume claim to claim that storage, that persistent volume, and then they can mount it in their pods and use it in their containers. So dynamically provisioning persistent volumes using storage classes. So a storage class is just a resource that describes a type of storage. So as a cluster administrator, what you can do is you can create multiple storage classes with different provisioners and different properties. For example, here's one storage class that on a slide that uses Azure Disk as its provisioner. So this is running in Azure, I guess. There's a specific SKU name. So these parameters are then dependent on the provisioner that you're using. So in this case, we have the SKU name, we have the location, and then we have the storage account, right? So if you're using a different one, you probably have different set of parameters. Now, Kubernetes also implements something that's called a container storage interface, or CSI. And CSI describes a standard way for exposing storage to containerized workloads. So what you could do is you could use this interface and then write your own and deploy your own plugins that can expose any new storage systems. So can I claim a specific persistent volume that my container used at last runtime or the PV that owns my database field? So I think what you're getting at will be, I'll explain that when I'll talk about StatefulSets. But yes, you can, there's a way for you to say this specific, not necessarily container, but this specific pod, I want this specific pod to use this specific persistent volume, and this other pod, I want it to use this other specific persistent volume. And I'll talk about that. That's where StatefulSets comes in. There's also different access modes that you can choose from. Read, write once, where the volume can even be mounted, and then read and written by a single node only. The second option is the read only many, where the volume can be mounted as a read only volume by many nodes, or read write many, where the volume can be mounted as read write by many nodes. Now, when deciding on these access modes, make sure that read the documentation of the volume plugin that you're using, because not all of them necessarily support all of these access modes. So here's the YAML for the persistent volume that uses the manual storage class. It specifies the storage capacity and then the access mode, as well as where it's going to be mounted on the host path. So how you go about claiming the persistent volume, right? So this claim on the slide, what we're doing is we're requesting 1 GB byte of storage using the manual storage class name and the read-write only, read-write once access mode. And then this exactly matches the persistent volume, this one that I had on the previous slide. Finally, how do you mount it into your pod? We've talked about this last time. You create a volume, you name the volume, and then you say, I want to create I want to get this volume through a persistent volume claim, line 13, and then you're just specifying the claim name, and then mounting the actual volume is exactly the same as in previous cases. Okay, so let's do volumes, persistent volume claims, demo. Actually, you know what? I'll skip this demo. There is a demo in the on Notion, but let me skip through that one because just looking at it, and it's pretty much what we did last time with secrets. So there's a lot of value there. So let me just go continue with the stateful workloads, and then I'll do a longer demo for the stateful workloads, right? So using the persistent volumes and the volume claims, what we could do is we could run multiple pod replicas using a replica set, right? These replicas will have different names and IP addresses, but other than that, they're exactly the same. So let's look at this same example that I had a couple of slides back, right? So the volume and the persistent volume claim are both defined in the pod spec. And this is the template that replica set uses when creating new pods. So what's the actual problem here? The problem here is that if you have a single pod, it will reference a single persistent volume claim and a single persistent volume, which might be perfectly good and well. However, the problem is when you scale the pods, each new pod that gets created will get a different name and it will get a different IP address. And since you've included the persistent volume and persistent volume claim inside the pod template, all replicas will use the same persistent volume claim and the same persistent volume as shown on this slide. Now, because we've defined the reference to the persistent volume claim in the template, we can't really make each pod replica use its own persistent volume claim. For that reason, we can't use a single replica set to actually run something like a distributed data store where each pod has its own storage. So we'll show you how you can do that. Now, there are a couple of solutions, or rather than solutions, they're more like workarounds. So what you could do is you could create the pods manually, right? And then have them use separate persistent volume claim like that. However, you don't want to manage your pod's lifecycle manually, right? Remember that any manually created pod will not get automatically restarted when or if it crashes. Another workaround here would be you could use multiple replica sets where you could create a replica set for each one of your pods. So this solution could work, but it is going to be painful to maintain, right? And it loses its, that's not the reason why you would use a replica set, right? Now, in addition to just having separate storage per pod, what you also need to make sure is that you have a stable and persistent identity. So what I mean by stable identity is that if your pod gets restarted, if it gets restarted, it has to come back with the same identifier, which means the same name and the same IP address. Now, the reason for this stable identity is that you often need to address a specific replica, right? Especially when you're running something as a storage system, right? As a database. If you have multiple replicas, there are cases where you want to target a specific replica, right? And that is very complicated to do if you don't have any stable identifiers and if your IP addresses and names change every time something is restarted. I hinted towards this already. There is a resource called StatefulSet, which is a solution for this. And you can use this resource for any applications that require a stable name and state. So the main difference between a stateful set and a replica set is that when the pods that are created by replica set get rescheduled, they will always get a new name and they'll get a new IP address. And you've seen this over the past couple of weeks as we've been talking about everything, right? This was the normal behavior, right? Every time we restarted a pod, we would get a different name and we would get a different IP address. Now, StatefulSet, what it does is it does actually the opposite, right? It will ensure that the pod will keep the same name and the same IP address even when it gets rescheduled or restarted. So if we create a pod called MongoDB-0 and we restart that pod or delete that pod, StatefulSet will recreate the exact same one with exact same name and with exact same IP address. So I was talking one-to-one, but you can also run multiple pod replicas with StatefulSets, right? Now, the thing here is that these replicas are not the same as with replica sets, right? With replica sets, when you scale from 1 to 5, all those 5 pods are exactly the same, right? They share everything. They have different IP addresses, right? But they're exactly the same. With stateful sets, they're not exactly the same when you scale them up because they can have their own set of volume claims, meaning their own set of volume claim templates, right? They don't have random names. Instead of a random name, they actually, each pod that's part of the stateful set gets an index assigned to it, right? I've also mentioned that sometimes when, in some of the scenarios, you want to be able to address a specific replica from the stateful set. When using a replica set, we said that IPs are unique, but they'll go away and they'll be different when the pod gets restarted. StatefulSet, you'll get a persistent IP address, which means that you have a way to address a specific replica, right? The way that you could do that is you could create something called a headless Kubernetes service, and then you can use the pod name identity, right, to actually address a specific pod versus a service. I don't know if you've heard about the pets versus cattle analogy, right? But you can also think about stateful sets as pets and replica sets as cattle, right? Because for apps that are stateless, it is actually fine and it is desirable to treat your instances as cattle, right? So if one of the instances dies or crashes, you can replace it and no one will know about it, right? It'll be a different name, but it'll be the same thing, right? However, with stateful apps, the instances are treated more like pets, right? You just can't easily replace them without people noticing, right? What you need to do is you need to replace it with an instance that looks exactly the same and behaves exactly like the old one. And in our Kubernetes world, that means that it has the same name and it has the same identity. Okay, also stateful sets also ensure that the pods get rescheduled in such a way that they'll keep their identity and state. So this is all baked in, and they have their own sets of volumes and everything. Okay, so let's look at how the resource looks like for a stateful set. It looks very similar to a replica set. The critical difference here is on line 5. Where the volume claim templates, and this is the section where we actually defined the template for the persistent volume claim. So when the stateful set needs to create a new pod replica, it will use this template to also create a persistent volume and persistent volume claims for each pod. as shown in this slide, right? So you have a stateful set that contains a pod template as well as the persistent volume claim template. And then when you create these different pods, when you scale it up, each one of these pods will have its own persistent volume claim. So they'll each separately claim a piece of volume, and they'll also have its own persistent volume as well. So there'll be like 3 separate independent replicas if you wish. Okay, now let's go to a demo. Just reconnect my Cloud Shell. And I have to switch as well. Perfect. All right, so I have a Kubernetes cluster. No, let me authorize it. This. Okay, it's an empty cluster. So the first thing that I will do is I will create a headless service, Kubernetes service called MongoDB. Notice that the cluster IP is set to none, but the ports will be, the target port will be targeting the pods that we'll create by the stateful set. So let's create this one. So what this means, the headless service, is that this service won't have any cluster IP set at all. It'll just be used as a selector to the stateful set pods that we will create next. Okay, let's create a stateful set now, and I'll copy paste it and I can talk through it. Okay, so stateful set, we're calling it MongoDB. We're specifying the service name here. So this is that headless service that we've created. Match labels. We have the template for our pods, just running a Mongo container, exposing 27017, and then we're mounting a volume called PVC to /data/db. That's where the MongoDB looks for the database. This last portion here is the actual volume claim template, where we're saying for each pod that you're going to create, use this template when you're creating the volume claims, right? So the volume claim will be called PVC. It will have the read write once access mode set, and we're requesting 1 GB of storage. So let's create this one, and let's list the pods. Still pending. I'll take a couple of seconds. But notice, this is the first thing that you'll probably notice right away is the name, right? If we would create just like a normal deployment, we would get that random string there for the replica set and the pod as well. However, this time we just got the name of the stateful set with a index number, right? So this is just saying this is MongoDB with index 0. So there's the first MongoDB pod that's running. So if we scale this, so let's scale StatefulSet called MongoDB, and we'll scale it to, say, 4 replicas. Let's list them. Might take a while. But you already see that the second replica that's coming up it's called the exact same way. The only difference is it has an index of 1. Let's do that again. So it's creating it one by one. Let me also list the pods with labels. Whoops, labels. Selector MongoDB. There's the pod name is specified in the labels here. You'll see the statefulset.kubernetes.io/pod name, MongoDB1, MongoDB2, Mongo 3, 4, and so on. So let's see how we can actually access these. So all 4 of them are now up and running. So the way that we can access these pods directly, address them directly, is by using the format of pod name dot that headless service name that we've created, right? dot, then we have namespace, SVC, cluster local, right? So it's similar to as you would address the service. The only difference is that you're going to use the pod name before the headless service name. So let's run a Mongo shell, and then we'll try to access 4017, and we'll try to access different replicas from within this shell. I tabbed away from my notes. Okay, so let's do bin bash here. Get the shell. Okay. All right, so now I'm inside a Mongo shell, and from here I have access to the Mongo shell that I can run, and I can use Mongo. And then if I want to connect to the first replica of the pod that we've created, that's called MongoDB-0. .mongodb as the service name, I can use the Mongo binary and then just connect to that instance of the Mongo database that's running. I am automatically connected to a test collection, I think. So let's just insert something here. Let's say hello first instance. So let's do this, right? So it's saying that we've inserted one entry. Also try to find it. You'll see that there's, let me tab up. This is the record that we've created. It got the automatic object ID assigned, and then we got the name that we've set, right? So if I exit out of this Mongo, this was the Mongo 0 instance, right? So let's connect to Mongo, let's do Mongo 2 instance. It doesn't really matter, right? We have 4 of them, right? If I do the same find here, this time there's nothing, right? Of course, because this is its own pod that has its own PVC that had its own volume provision for it, right? So each one of these pods are actually separate replicas. They're not using the same volume underneath. So same thing. If we insert stuff here, we'll say some other instance. If I can type, go, write result 1, right, and then db, let's see, db test find, right, some other instance, right. So let's go out. So this was MongoDB 2, and then we had MongoDB 0, right. So let's delete the MongoDB 2 instance, right. So this was some other instance that had that data set in. So let's delete this one, and I'm just gonna watch the pods down here. You'll notice that it was getting terminated, and then pending creating running, what we got is we ended up with MongoDB-2 instance again that has the same name. Forgot to show you. It also has the same IP address, right? So if we try to connect back, so let's do this guy again, and then we will connect to instance number 2. So we'll say MongoDB 2.MongoDB. So this is then .svc.default.cluster.local, right? Oh, what did I miss? Of course, it's service namespace.svc.cluster.local, right? So I get into the same thing. And now if we do db test, is it db test find? You'll notice that it says, let's do here. So it says some other instance. So this is the same data that we entered in earlier. Then we deleted that same pod. The pod came back up, and the data was still there. All right, so let's take 10 minutes, and then you can go through. This is exercise number 2 or lab number 2. If you want to go through lab number 1 as well, it's very short. It's just volumes. I don't think there shouldn't be anything new for you, especially if you were here last week when we talked about configuration. But feel free to do that as well. But MongoDB and StatefulSets is number 2, and then we'll be back in around 10 minutes. All right, so Marcel brought up a good couple of good points that I should have had on the slides in regards about deleting the persistent volume and persistent volume claims. So if I list the persistent volumes, right, so these are the five that were created from the demo, right, you'll notice that there's a setting called reclaim policy, and this one is set to delete. The other value here is called retain, I think. So that just controls if this persistent volume will get deleted or not when you delete the claim, right? So you have to delete the claim in order for this reclaim policy on the volume to kick in. Now, the PVC, the claim, is not bound to the pod's lifecycle either, right? So if I list the pods here, so I have 4 of them, and I say, let's scale the StatefulSet MongoDB replicas. Let's scale it just down to 1, right? So these are being terminated one after another. However, if we list the volumes, so all the volumes will stay. Also, all the persistent volumes will stay as well, right? So these will not get deleted, right? These will only get deleted. Actually, the volume will get deleted whenever you delete the claim. So the way that, so should this be done by Kubernetes operator? It could be done by an operator, but I'm pretty sure there has to be a solution for this somewhere that takes care of this for you. Like, how do you want this to be controlled, right? But also, you might not have. Yeah, I think there's probably a tool. I'm not aware of the tool specifically, but yeah, something like some operator would definitely be a good a way to do this, right? Where you could configure it in such a way that it periodically cleans up your PVCs, and then the PVCs will clean the volumes as well. Yeah, also, this is, if I list the persistent volume claims, you'll notice that all the status for these ones is saying that they're bound, right? So they're bound to each specific volume, right? And these are all dynamically provisioned. You can see this by the names here, the storage class that's used. Also, if you go to Kubernetes, if you go to Google Cloud Platform to the UI, and then go under the storage of your Kubernetes engine, you can see all of those claims here as well, right? So you can look at them, look at the details. I mean, right now it just shows you the YAML. It's just a view thing. You can't actually, I guess you can delete them, right? You can delete them, but you can't create anything. Yeah. All right. Let's switch to. If I can find my slides. There you go. Okay. All right, so let's change gears and let's talk about service accounts a little bit. All right. So service accounts in Kubernetes, there's just another set of resources like pods and deployments that get created and managed by Kubernetes API. They are meant to be used by pods to be able to authenticate to the Kubernetes API server or to any external services. A default service account will always get created for you whenever you create a new namespace, right? So that default service account is then used for all the pods that run in that namespace, unless you explicitly specify a different service account to be used by your pods. So up until now, when we've been creating deployments and pods, we've never mentioned service accounts, right? And this was all done automatically for us by Kubernetes, right? So whenever we created a pod in a certain namespace, Kubernetes checked, noticed that there's no service account assigned to it, and it just assigned a default service account that's running in that namespace, in any namespace in Kubernetes. As for the resource itself, the service account name has a name, a namespace. It lives in a namespace. It can have labels and annotations. Additionally, it has fields such like image pull secrets, mountable secrets, and the tokens section. For example, what you could do is you could define image pull secrets. So if you remember, image pull secrets are your Docker credentials, pretty much, the credentials that Kubernetes can use to pull images from your private container registries. So these are then used by pods, right? So if you would define these, each could define these image pull secrets inside your service account, and then any pod that's using that service account will have access to those pull secrets. So if you're using like private registries, it'll just automatically pull the images down for you, so you don't have to set a image pull secret separately for each pod or within each deployment. Similarly, the mountable secrets field is just specifying the secrets that can be mounted by the pod using the service account. And then the tokens field will just show the list of all authentication tokens that are available in the service account. Also, Kubernetes will automatically mount the first token inside your pod so you can access it in your containers. Now, the mountable secret from the account, the service account, that's the default token, right? So that's line 7 in that listing down there. That gets automatically mounted under var run secrets Kubernetes IO service account, right? The secret then, this default token secret, has an authentication token that gets mounted as a token file. It has a namespace name that's mounted as a namespace file with the value of the namespace name. Say that 5 times quickly. And it also has a public certificate authority of the API server, which is mounted as a ca.crd file. So what can you do with these service accounts? So Kubernetes uses different authentication mechanisms or plugins. So it can use client certificates, it can use bearer tokens, authenticating proxies, HTTP-based auth, all these different plugins to authenticate API requests. So whenever the Kubernetes API server receives a request, the request will go through all these proxies, so all these configured plugins, and then these plugins will then try to determine who is sending these requests. They'll try to authenticate the sender, right? So the plugins will, one after another, try to extract the identity of the caller from the request. And then the first plugin that's able to extract that information, the first plugin who can say, yes, I know who this XYZ that's calling me is, then they'll send the request to the API server, right? And then at this point, the request will continue to the authorization phase where based on the authentication information, right, the authorization phase will determine if that principal can access or do the certain action that they want to do, if they can list something, or if they can create resources, or if they can delete resources. So the identity that gets extracted by those plugins consists of a username. So that's just a string that identifies the user or the caller, the user ID. This one is more unique than the username. Groups. So there's a set of strings that indicate the groups the user belongs to. So this could be groups like developers, administrators, testers, etc. And there's a bunch of other extra fields as well. Now, the service account username uses the format as shown in the slide. So system : service account : namespace of where the service account is running in or created in, and the actual service account name. Now the API, the Kubernetes API server will then use this username to determine if the caller, so the caller here is the process that's inside of your container, if the caller can perform the specified action. For example, can the caller or the process list the pods from the API server, or can they list the namespaces or create deployments, etc. So each one of these service accounts can belong to one or more groups. So these groups are then used to grant the permissions to multiple users at the same time. For example, if you, pretty sure you've heard about a group called administrators, right? And if you're part of that group, you pretty much have access to everything. You have administrative privileges to probably to everything in that system, right? But of course, like there's other groups, developers, testers, QA, whatever you want, however you want to slice your system up, right? But in the end, for Kubernetes, these are just simple, unique strings. Okay, let's look at the quick service account demo. Let me switch here. Let me just delete the StatefulSet MongoDB. Okay, and then we can go to service accounts. Okay, so let me, shouldn't be, okay, so this one's being terminated, but let me just list get service accounts, right? You'll notice that there's one service account in the default namespace called default. And then similarly, if I would do get service account and the cube system, right? There's a bunch of them here as well. There's also a default one, right? But there's a bunch of them here as well. Practically, if you're creating pods, you should always create corresponding service accounts for your pods, right? You should not have your pods reuse the same service accounts. Let's put it deployment, right? In your deployment pod, in the pod template within your deployment, you should have a unique service name that's being used, and you should not reuse that service name across different deployments. So let's run, just run simple pod that runs an nginx image. So the container is being created. Now, if I show the YAML representation of this pod, you'll notice up here, there's the service account name, and we haven't set that, right? This is something that Kubernetes set for us automatically, right? It just sets the service account name to default. And then down here under volumes, you'll notice that it actually creates a volume that can then be, it's then mounted under var run secrets Kubernetes IO service account folder, right? So that's the token from that service account that gets mounted automatically into each one of your pods. So let's go inside this pod. And then if I look to var run secrets, Kubernetes IO, service account, you'll notice that there's the CRT file, the namespace, and the token. So what I'll do is I'll just take this token and store it into an environment variable because we'll use it to make requests. You can look at the token contents if you want. So let's do, actually I can just do this. It's not, hopefully no one will, oh wait, I did something wrong. So let's do token, var run secrets, Kubernetes.io, service account / token. Okay. Oh, I should do an echo, of course, not cat. So if you go to jwt.io, this is just a debugger for your JWT tokens. You'll notice that down here, it's saying that this is the services account namespace, this is the secret name, this is the name of the service account, account UID, and then the actual name, right? So this is that system service account namespace and the name of the service account. Okay, so let's go back. And I am still inside the pod. So what we can do from here is we can make a request, and we'll pass this token as a bearer token, and we can make a request to the Kubernetes.default. So there's a service called Kubernetes, right, that we can access, running in the default namespace. And you'll notice that we get back the response, and this is my server's address, right? Now what we can do with this is we can actually make calls to the Kubernetes API, right? So let's do API v1 namespaces. And this is all, like, this API is well known, is well defined and documented on, if you go to Kubernetes IO. So default namespace, default /pod/simple pod, right? So let's try to get information about the simple pod, right? We get an error because it's saying that simple pod, so this is our principal, right? This is the caller, right? So we are forbidden, right? We cannot, this user with this name cannot get the resource pods in this API group. Well, I actually misspelled the namespace name, but it's the same thing, right? It's basically saying that user cannot access the pods resource in this API group. It's forbidden. We cannot do that. Is it a good idea to use service accounts to separate environments? I guess, I mean, I would do it per deployments, not necessarily per environments per se, because imagine if you, as long as you don't have any more, like any additional layers within the environments, let's say if you have in your production environment, if you have multiple deployments, and then if you're using the same service account for all of them, what happens if, like, should all of your deployments within the same environment have access to everything? Or should some of the deployments be like more restricted than the other deployments? Right, so I guess that's the question that you have to answer, right? But I'm always wary about, like, when it comes to security, of course, reusing stuff at such a broader scale, you know, because once you do this, it's going to be very hard for you to say, oh, now I'm going to lock it down. Like, now I want this deployment to only have access to this one thing and then prevent everything else. Then you'll have to create a separate service account for that one. And then you're already like, oh, but we had it per environment. Now we had it per environment. But then also within this environment, we have this one special service account. It can get complex. I mean, I think it would be easier to just say any new deployments that you're creating have to have their own service account, period. That's it. Even though those service accounts might have the exact same permissions, right? But at least it gives you the ability to fine-tune these things later on if you need to. Hope that answers the question. All right, so this is basically saying we cannot access the we cannot access that API because we don't have permissions for it, right? So what we need to do here is we need to find a way how we could add this default service account or a different service account again to some group that might have access to this API. Now, adding the default service account within a namespace to giving that default service account more permissions or giving it to adding it to a specific group, I wouldn't do that. As I said, I would rather have, it's better to create a separate service account that's specific to what you're trying to do and then use it like that. Yes, I will update the Notion with that, with my comment. Okay, let's quickly switch back to slides and we'll talk about the role-based access control. So the question that we had in the demo is, how can we manage the roles, right? And how can we grant access to that specific service account, right? How can we grant some extra access to service accounts, right? And the way to do that is through role-based access control, or RBAC. So Kubernetes controls, any access to resources is done through roles, right? And the system that's being used is called RBAC, role-based access control. And using this, you can dynamically configure policies, certain policies, and then that way you can control access to Kubernetes resources. There are actually 2 Kubernetes resources related to RBAC, right, functionally, but if you count them, they're actually 4, right, but they're very, very similar. So there's a role and a cluster role, and there's a role binding and a cluster role binding. Let's look at each one of them separately, and I'll explain what the difference is between role and a cluster role, and role binding and a cluster role binding. But in short, one is for cluster wide, the other one isn't. Okay, so the role resource, what it does is, so this resource contains the rules that can represent a set of permissions. So the role is defined on the namespace level, and the rules only apply within that namespace. So if I would create a role in namespace A to restrict something, right, those restrictions will not apply in namespace B because I haven't created the specific role there. However, this is where you can use a cluster role to create those rules, and then those permissions will then apply cluster-wide, so across all the namespaces. The other couple of use cases for when you would want to use a cluster role is if you're defining rules for like a cluster scoped resources, for example, like nodes, right? You could then apply the rules for these namespaced, you can apply then the rules for the nodes across the cluster. The other thing that you could do is you could apply the rules for some namespaced resource, right, across all the namespaces. So you can say all the services in this cluster can only do, like, here are the roles for all the services in any namespace across the whole cluster, and then you would use a cluster role to do that. So if you think back to the demo that I did, right, when we tried to curl to that API and list the pods, and it didn't work, right? So the way that we could make that work, or the way that we would make that work, is we would define a role. Let's say I'm calling it here a pod reader role, and that role would grant me read access to pods, right? So this is the example of a role that would allow me to do that, right? So let's go through this one. API version is just a core API group the role will apply to, right? We've seen this. Then we have the kind of the resource, the metadata, right? The namespace, etc. And then under rules, if you look at the API rules, we have the API groups, right? So this is where we can say we want to apply this rule to all API groups, right? If it's, well, not all, but to specific API groups, right? So if we don't specify anything here, line 7, right? It's just going to apply to the core API group for pods, right? The way that you can get these API groups is if you can run the API resources command, right? And then in one of the columns, you'll see the name of the API group, and you'll also see the supported verbs, so line 9. So you'll also see what kind of verbs does that specific API group support, right? So an example for deployments, deployments will be under an API group called apps, and then that API group has verbs create, delete, list, update, watch, and a couple of others, right? Now, pods are part of the core Kubernetes API, so we don't have to specify any, we don't have to specifically call out any API group, right? So that's why that API groups field is empty. Line 8, on line 8, the resources. This is the field where we can just specify a list of resources we want to apply the rule to. And in this case, we're just setting it to pods. If we wanted to apply the same rule to any other resource from the same core API group, we could add the name of the resource there. Like we could add the pods, or we have the pods like services, config maps, secrets, and things like that, right? And then verbs is just saying you can get, you can watch, and you can list resources in this specific API group. This is what this role defines. So it's a pod reader. So someone, a principal that can read the pods, right? Here's another example where we have the API group set to apps, because that's where the deployments resource is in. And then what we're doing here differently on line 9 is we are specifying an exact resource name we want to apply this role to. So if there's a resource called my deployment of type deployment in the default namespace, then this role will apply to that specific resource name. Now, just creating this role alone is not gonna grant any permissions, or it's pretty much not gonna do anything, right? So you need to create, once you have this role, you also have to say who are the groups or users who have this role, right? Who have the role of, what do we have? Pod reader, for example. This is what the resource called role binding and cluster role binding do. So you would use these two resources to bind the permissions from the role resource to the users or the principals, right? The user in this case, right, is service account pretty much. Just like with the role and cluster role before, the role binding grants the permissions within the specific namespace, whereas the cluster role binding will do it cluster-wide. So if we go back to the pod reader role that we've created, so this is how we could bind that pod reader role to a service account called pod reader SA. So we have this role binding, same namespace, default namespace, and then under subjects, we're specifying the subject for that we want to bind this role to is a service account with the name podreader-sa. And then on line 9, 10, 11, 12, we're just referencing a role, which is podreader, right, and kind, and then the API group of that specific resource. So here's a more graphical representation on how these different resources are tied together. So the pod reader resource, which is a role, is going to define the rules. So we're just saying a rule that says you can do these three things. You can read the pod, right? You can list the pod. So that's the role. Then with using the role binding resource, we are saying we want to connect this role to this specific user account, right? So we want to grant, in a way, permissions to this subject, which is the service account, to have that role as well. Then finally, any pod that we start that has that pod reader SA service account will, because of that binding, belong to the pod, have the pod reader role, meaning it'll be granted those permissions. Let's continue with the demo and see how this looks like. So the first thing that I'll do is I will create a service account, a new service account called podreader-sa, the one that we had in the slides. So going back to, I don't know who asked the question. Was it Marcel? Yeah. Was it Marcel or, oh, it was Nikolai. Yeah. Going back to having like separate service accounts for environments or pods or deployments. this is all it takes to create a service account, right? So it's not like it's it's not like it's like this elaborate, resource that you have to create. It's literally like 4 lines, right? So it's fairly easy. And once you do it automatically, right, it's like, oh, every deployment should have a service account associated with it. It becomes second nature. Okay, so we created the service account. So if I list service accounts, I have the default one, which we're not going to use, right? And I have this pod reader service account that I just created. Now, once we have that, let's also create a role called pod reader, right? That applies to pod and allows us to list the pods. There's also a way that you can use kubectl, the CLI, to create the role. So you can say create role name and then specify these values through command line if you want. So we have the role, we have the service account. The next thing that we have to do is we actually have to tie those 2 things together. So let's do that. So creating a role binding that binds pod reader role to this service account, right? The pod reader SA. So let's do that. So role binding, right? It shows us here. We can describe it. Right? It shows you the service account, right? Who's the subject of this binding and what role does it have or does it grant? So once we have that, we can then create a pod. So let me delete this old pod. Delete simple pod. So this is the one that I've created. Get pod, delete pod, simple pod. So once this is deleted, we'll just create another one that actually has that pod reader SA service account. So we'll specify the service account explicitly. There you go. It's just an Nginx image, and this is the actual line where we're saying we want this pod to use this pod reader as a service account. So let's do this. Okay, so now if we go inside that pod, bin bash. So this is the same pod that we were in before. And then let's store the token, run secrets, Kubernetes IO, service account, token, okay? And then if we make a request to the API server, authorization, bearer token, so we're just passing this authorization bearer and the token as a header. And then we're calling Kubernetes service at default 443 API v1 namespaces default pods, right? So what we did is we added the verb called list, right? We added that to the role. What did I mess up? Okay, who can find an error? Where did I mess up? Curl, so bad, illegal. Okay, Kubernetes. Let's try this first, just to make sure that it's there. Okay, so the token is there. Okay, I probably typed it, messed it up somewhere. So it's curl, probably messed it up somewhere here. Bearer token, API v1 namespaces, default pods, and this actually gives us a response back from the API server, right, with all the pods that are running, which is just a single pod that we have, but we get all the details. Now, if you wanted to get the specific information about the specific pod, right, this is not going to work, right, because we do not have permissions to, I think get is the verb, right? We don't have permission to get the specific pod. We can only list the pods in that namespace. if I go out here, the other thing that I wanted to show is where you can actually look at the, let me see the command. Yeah, so I wanted to do this resources wide. So this is where you can see, might not look easy to read, but this is where you can see that API version. And this is where you can see the verbs that each resource supports. And this is where you can look at to, let me try making this a little bit smaller just so it fits, and then I'll change it back. This is such a wide output here. All right, no one can read it, but this one shows you the third column shows you the API version for all of the resources. And also shows you here at the end verbs that you can use, right? So for example, let me see, for namespaces, the verbs that are supported are create, delete, get, list, patch, update, watch, while for some of the other things, like there's a delete collection for ingresses, for example, or for node metrics, you can only do get and list, right? So the command is API-resources, and then you just do the wide output to see the different roles, the different verbs that are supported for the resource. Okay, let's go to the lab. So this is lab number 4, and I'll switch 10 minutes on, and then we'll come back and we'll talk about the network policies next. So see you in 10 minutes. All right, so let's go. Let's continue then. As I said, this was just me trying things out, what works best. Like if you all prefer me just talking, doing the demos, and you go through the labs later, that's completely fine by me. The reason that I did it this way is because this hopefully forces you to do it right now. Like I know I've been in situations where I'm like, oh yeah, I'm going to do it tomorrow or later, and then that never happened. All right, anyway, let's continue then, and I'll talk about network policies next. And network policies, well, with network policies, what you can do is you can control how the traffic flows between the applications in your cluster at the IP and the port level. So a resource that's called network policies. Network policy can be defined, and it can configure how your pods can communicate to other pods within the cluster. So when you're creating a network policies, there are 3 things you need to do. First, you need to select the pods you want the policy to apply to. Of course, the way to do that in Kubernetes is by defining labels. Defining labels match selectors. For example, we could define the label called app equals hello world, and that will apply the policy to all the pods that have that label set. Next, you need to specify the location, I guess, where the policy applies. So what I mean by location, I don't think location is a good word, but direction, I guess. Yeah, direction is better, right? So you can apply it either to traffic that's coming in to your pod, so any clients that are making calls to your application, or you could apply it to the traffic that's going out of your pod, so anything that your application calls out to, or you can apply it in both directions. So we selected the pods that the policy applies to, we selected the direction that the policy applies to, and then finally what you have to do is you have to be specific and specify which pods or IP addresses can the calls be made to or from. So you can use different selectors here. You can, for example, select the client namespaces. You can select the namespaces your clients are coming from, or pod labels, or you can even specify IP blocks. So let's look at this on an example because it's much easier to understand. So note that this is not the full YAML for this resource, but it was so long that I had to split it over a couple of slides. So there's the first part here, line 7, is telling us that first thing, right? It's telling us that this policy applies to all the pods that have the app hello label set, right? Because we've created the policy in the default namespace, so line 5. We're saying that this policy will apply to all the pods that have that label set. Then on line 10, we're selecting the policy types. So this is where we're saying that this policy applies to both ingress and egress traffic. So ingress being incoming, egress being outgoing traffic from the pods that match the app hello label. Then in the next section, we have the ingress rules. So these are the rules for incoming traffic to the pod. So what we're saying here that the calls can be made from any IP within that defined IP block. So that's the first one on line 5. That's like, I think that's like 65,000 IP addresses, right? So the calls can be made from any of those IP addresses except line 6, except for pods whose IP addresses fall within that specified block. So that's 172.17.1.0 and all the way to 1.255, right? And also, the callers have to be any pods that are labeled with the version v2 label. And the call has to be made on port 8080. So, so the first section is saying apply everything to app::hello pods, right? So someone is trying to call me, I'm the pod hello, right? Someone's trying to call me. Who can call me is any pod with version v2 label set can call me on port 8080, but also their IP address has to fall within these IP blocks, right? Within this first IP block, except the section of those IP addresses. So this is intentionally made complex here, just to show you that how fine-tuned you can go with these rules, with these policies. But practically, you might not be as specific or as detailed here. You might just say, hey, any pods with label environment prod can call to environment prod, but pods with label test cannot call into the prod, for example, right? So here's the visual representations of this one. So on the right side, we have that network policy that encompasses the pods that it applies to. So those are all the pods with the app hello label set. And then on the left side, we just have that single pod that happens to fall within that defined IP range that we created or we define, right? And also has that version v2 label set. So that pod can theoretically call our app hello pods, right? So on the first example, that first green line, right, the pod on the left is making a call to port 8080 on our pod. Now, because that's something that we explicitly allowed in the policy, so we explicitly said on line 13, port 8080. On line 10, we said version v2 has to be the calling pod, and it also has to be from one of those IP addresses. Because all of those things are true, the call can be made, right? So that's the first green line. The second one is red. In the second one, what this pod is trying to do is trying to make a call on port 3000. However, because we haven't explicitly allowed that by the network policy, we haven't called out port 3000 anywhere, right? The call will be blocked. So even though the calling pod satisfies all those IP labels, everything, but it doesn't satisfy the port that it's trying to call. So it's going to be blocked. And then finally, the last example is just to show that if the network policy does not apply to any of the other pods, it doesn't really matter, right? Nothing is restricted at that point for those pods. So this was the ingress portion. There's also the egress portion that applies to the outgoing traffic. So this is saying, what can I me being that pod, the app:hello pod, right? What can I call out to, right? So what this policy is specifying that that pod can make calls to any IP address that's within that IP block, but only to port 5000, right? So the pod can only call out to those specific 256 IP addresses, and it has to be on port 5000. If it's not port 5000, and if it's not any of those IP addresses, it's going to be blocked. Looking at an example, so in the case of these egress rules, right, the pod that's being affected is us, right? So the rules are applying to our pods on the left side. First example, we're trying to make a call to the IP address to the pod or service with that IP address on port 5000. Is it 5000? Yes, on port 5000, that's going to work because it falls within the rules that we define. However, the call on port 3000 will not work because we explicitly called out port 5000. And then on the bottom example, we are calling out to port 5000, that satisfies the rules. However, the pod's IP address is outside of the defined IP range, so that call is going to be blocked. Okay, so the way these network policies are implemented and enforced is through network plugins. Meaning, if you do not install the network plugin on your cluster, the policies that you've created won't have any effect because there's not going to be anything that will enforce these rules. Now, these plugins, a couple of examples are Cilium, Calico, and there's a bunch of others. We're going to do a lab. I'll show a demo on Cilium and how to install this, but installing and configuring any of others is probably very, very similar. Also, there is an interface called Container Network Interface. So when you're looking for these plugins, just make sure that they implement this Container Network Interface, right? So there's a lot of these, like we talked about the storage interface, right? There's the Docker runtime interface. There's a Container Network Interface. So Kubernetes just calls out to these define interfaces, and then Kubernetes doesn't really care what implements that interface underneath, which makes it extremely pluggable, right? So you can create your own container network interface if you want to, right? Nothing and no one is preventing you to do that. You just have to satisfy that specific interface. Okay, let's do the network policies demo with Cilium. So let me switch. Switch to the notes here. Yeah, this, like, it's almost like each one of the things that I talked about today could be like a 3-4 hour session on its own, because like we're just scratching the surface here. But yeah, it is extremely, it can be complex. And we haven't even talked about CRDs, and we'll spend like 30 minutes on it, and that's like a huge topic as well. Okay, so I think I downloaded Cilium already. Let me see. Or maybe I didn't. I thought I did. Oh no, I didn't. Okay, so let me download Cilium. Okay, let's do that. And all these commands are in the in Notion. Okay, so I have Cilium downloaded. So I'll just do is Cilium install. I'll just install it, right? Oh, that's nice. So the required property project is not set. Oh, okay. I have to set the project. So what was let me see. I always forget what the command is, even though it's always telling me what it is. So start Kubernetes. Kubernetes, I think. Yes. Oh no, wrong one. Let me check what my project name is. I thought it was Start Kubernetes. Oh, Start Kubernetes Live, maybe. Let's see. No. Okay, let me give me a second to figure out what my project name is. Google Cloud Console. Oh, it's Start Kubernetes Live without the dash here. Yes. All right, so we have the project set. And now that I have the project set, I can actually call Cilium install. And this should now work. Yeah, so Cilium will automatically detect that we're running in Google Cloud, and I'll just do, you don't have to do anything, any additional configuration or nothing like that. Note that I'm not going to talk about Cilium specifically. I'm not going to talk about details on how Cilium works, what it does, what it installs. We'll just look at it as a black box, as something that can enforce the network policies that we will create, right? So this restarted all the pods and then created a bunch of things that it needed to create. So let's just do Cilium status.wait. So let me run this one, and this one will just validate that that the installation has completed. I can also list, yeah, there are still a couple of things that are being, I think, recreated maybe. Yeah, so there's Cilium. Yeah, so there's one that's still being started. Okay, now everything is up and running. Okay. Daemon set, containers, image version. Okay, so all is good. I think Hubble is like a UI. I haven't had a chance to look at this one as well, but it might be interesting to check it out, where you can actually visualize the network policies, I'm assuming, and you can see who can call which pod can call which other pod and addresses. Okay, so let's do a simple example. I will create a pod called egress pod. So there's nothing magical here, just a pod called no egress pod. And as the name suggests, what we'll do is we'll create a network policy that will prevent calls from this pod to anywhere else, right? So the pod could not call to anything else. So let's do this one. Now, if I go inside this pod, just want to show that I can do is I can curl to Google, for example, right? So it is saying move permanently, but I get like 200 back. And then if I just do curl up, -L, right? There we go, right? So I actually get back. It doesn't look nice, but this is the response from Google, right? So I get it back, google.com. So what we'll do now is I will create a extremely simple network policy. And just give me a second. Network. Okay. So I'm creating a network policy called deny egress. And that network policy will apply to all the pods with that hello label set, which is that single pod. And we're creating a policy for egress policy. However, we're not specifying any rules, right? Which means that since we're not specifying any rules, it will be denied by default, right? So we're not explicitly allowing anything to call out, right? So this is just locking everything down, right? So if I go back to no egress pod, if I try to curl again to google.com, and I want to just do this, you'll notice that this time it's not going to work. And after a couple of seconds, it'll time out, right? It'll time out, and it's only because that's because we created this network policy that denies any outgoing calls from the pods with this label set. Now, if I would create a pod that has a different label. Let's say the label will be goodbye pod. So let's do this. Just show how this works. So goodbye pod. The key is here in the labels, right? I'm just setting it to goodbye. So let's do this. So I do have two pods. Curling from this one doesn't work, but then if I try to curl from within the goodbye pod, this one works fine, right? So network policies are really a really powerful way that you can lock everything down. The way that you would do this is the way that I would do it, right? Is I would lock down everything, right? Like create a no egress policy, right? No egress policy that applies to all of your pods, right? All of the pods in the namespace, no one can call out. Then you can figure out, oh, okay, looks like this hello world pod or whatever it is, or this deployment is actually calling out to one of our API or api.github.com or something. Then you can go and modify your network policy to explicitly allow for that specific pod with that specific label to explicitly allow calling out to that api.github.com or whatever you've defined, right? And it's just a good way to like lock everything down and then slowly like allow calls between different pods or allow calling out, allow or deny calling in, and so on. Second window inside a Cloud Shell. Oh, it's so I'm using Tmux. I think Tmux runs by default here, but I have my own. What is it? The shortcut. So for me, I think it's control. Whatever your control combination is. For me, it's like caps lock and A, and my caps lock is actually control. So it's control A and then dash. So control A and dash will open it like this, and then control A and underscore will open it, I guess, at the bottom or somehow. Yeah, like this. So dash will open it horizontally, and then underscore will do it vertically. Yeah, good for asking this, and now I'm in like a window hell here. Let me. By the way, if you're not using Tmux, it did take me a while to get used to it, like with all the switching and everything. But it's really great and it's really good. Also for the network policies, I think there's a let me see network. I think someone was network policy. Let me try to find it. I know someone was. Oh yeah, there it is. Of course it was Ahmed, right? So Ahmed collects this. It's a GitHub repo. I can put it in Notion, right? But he has like a bunch of network policies that you might want to use, right? Like a simple things that you can actually go in and just copy paste stuff if you want to, right? For example, there's the deny all traffic to an application, right? And it has like a nice animation telling you what it actually does and then how you can actually configure it and how you can go and try it out, right? To see if it works. But yeah, basically the combination of like these things, you can really tighten up your security and everything. And this is something that you should, like if you are using Kubernetes and if you're not using network policies, you should be. It's one of those things that you should set up. I mean, imagine if you have, let's say someone gains access to one of your containers that's running inside the cluster, right? First of all, if you're using like a service account that's open, right? They have access to everything pretty much. Now, if you scope that service account down, right, to be very narrow, then they don't have access to anything, right? Or not everything at least, but you're minimizing the area that they have access to. And then additionally, if you have network policies, right, let's say you There's no way that your pods can call out to anything else, right? If you lock that down, there's not much they can do, right? But if you leave it open, they can call out to whatever they want, bring down, install their tools, do whatever they want to do, right? So it's just limiting their area of impact that they can have, right? All right, let's see what's next. Okay, so I'm not gonna take the break now or the time for the lab. So I'll just jump into the custom resource definition next, and then we'll do, I'll do a lab for that one. And if you guys have any questions, you can just ask in comments or in Discord, right? But let's go on to custom resource definitions, right? So up until now, we've talked about like a lot of resources, right? A lot of built-in resources, what they are, how to use them, how they work, right? But as always, and as with everything, right, you'll probably run into scenarios where these existing resources are either too limiting, or they're not precisely what you need to do, or they don't exist at all, right? So you need something more custom, right? And this is where these custom resource definitions, or CRDs, come in. And what this allows you to do is it allows you to create and define your own resources. Now you've seen when I talked about service accounts, how we made the calls to the Kubernetes API, right? So each resource that's in Kubernetes gets its endpoint in the Kubernetes API. So we're only calling out to pods, but you could call out to service account, deployments, services, or pretty much any resource, right? So all the operations and all this communication and let's say kubectl, right? So when you're using the Kubernetes CLI, you're actually talking to a REST API, right? So the API server inside Kubernetes is handling those REST API calls. For that reason, everything in Kubernetes is pretty much treated as an API object, and everything has an entry in the API, right? Which is really, really powerful. So Kubernetes is API galore, right? Everything is API. So an example, as I said, was when we're talking about service accounts, and I was making requests to /APIs, v1, so the namespaces, default, pods, right, or whatever the call was. So custom resources in Kubernetes, or custom resource definitions, they're the way that you would go about extending the Kubernetes API. So you could create your own custom resource. You could install that resource or create that resource definition in your cluster or in any other Kubernetes cluster. It's not tied to one cluster, right? Once you have the custom resource created or installed, the template for it installed, once the Kubernetes knows how to create instances of those resources, then you can create the objects, right? Using Kubernetes CLIs, kubectl create, or you can create a YAML, right? Just like you would do it with pods or deployments or any other Kubernetes service. So let's say we've created a custom resource that's called Hello World. You could then use kubectl get hello world or described hello world to interact with that object of the hello world kind, right? Of the hello world type that you've created. So Kubernetes does that for you automatically. So it creates that API for you behind the scenes. Now, just having this custom resource definition on their own, what you get is just a way to store and retrieve the data, right? There's no real logic or no power behind that resource, right? However, if you want to level them up and if you really want to make them powerful, you have to combine them with something that's called a controller. So using this controller, what you can do is you can define or declare your resource desired state and then keep your object's current state in sync with the desired state. So you could, let's go back to the hello world custom resource, right, that we've created, right? You could do some additional logic behind that once someone creates an instance of that resource, right? So if we think about, let me try to think about something more appropriate than hello world. I have to get better examples. Let's say you create a custom resource called a website, right? And that website resource, what it does, it takes in a GitHub URL, right? So we've created that. We have one field that says GitHub URL. You create the resource, and then nothing's going to happen, right? But what you want to do is when that resource is created, you want to pull that GitHub repo. You want to build that GitHub repo. You want to run a container that runs that website inside the pod. And then maybe you want to punch a hole through the Ingress gateway and expose it through the public API, public external IP address, right? Now, in order to do all that logic, that's like a custom logic, right? Kubernetes has no clue what you want to do with it. So this is where you would create a controller, right? And that controller has a loop, and it constantly watches, right? So it watches and it's saying, oh, is there a website resource that was created for me? Was there a website resource? As soon as there's a website resource that's created, the controller will pick it up, and then you have control over what you want to do, right? So someone creates a website resource. You, from the code, of course, you get notified about it. And then what you can do is you can then pull down the GitHub repo, right? You can build the repo. You can do whatever you want, right? Because you're running within the cluster. The controller is running within the cluster. You have access to the Kubernetes API. So you can do pretty much whatever you want to do. So let's do a different example that I'll do in the labs as well. So let's say we want to create a custom resource that's called a PDF document. So that PDF document takes in its definition, has a name of the document and some text field that's in markdown format. So what we want to do is, once that resource gets deployed to the cluster, we want to write a controller that will create a Kubernetes job. And within that job, we will have two init containers. One container will read the text from the resource. It will save the text into a markdown file. And then the second init container will use pandoc to basically convert the markdown file into a PDF file. In the pod, we'll also have the main container, which for our purposes will just be we'll just sleep within that container just so we can see that the PDF document was created. And in order to share the markdown file and then the PDF file between all the containers within the pod, we'll just use the volumes. So here's an example on how this PDF resource could look like. So it has a kind, it will have a version under metadata. You could do the name, the labels, annotations, anything, everything you like, and anything just like you would do with any other Kubernetes resource. Then under spec, we have two custom fields that we wanted to create. We have the document name. This is the name of the PDF file that we want to save. And then on line 6, we have the text field, which will just hold the markdown text that we want to store in or convert into PDF. Now, if you'll try to create this specification or this resource, we'll get an error, right? Because we don't have an API version, right? We need to tell, Kubernetes has no clue what a PDF document is, right? So we need a way to tell Kubernetes, hey, this is what this resource is about. Now, the way to do this is with the custom resource definition resource. So here's how this CRD custom resource definition could look like for this PDF document resource. So let's look at the names field first. So that's the line 10. That's a name. So this is where we're telling what the names are of our resource, right? As well as what the kind of the resource is, right? So kind is sort of like a type that's used across Kubernetes for all the resources. So the kind of a resource, we want to call it a PDF document. Then we have two fields called singular and plural. So singular is just a singular, is the name of a resource in the singular form, right? So it's a PDF document. So this will also allow us to do kubectl get, and notice I have an extra space there. Kubectl get PDF document, one word. This will allow us to list the resource. Under plural, that name would also apply to kubectl get PDF documents, but it also will be the name that shows up in the API endpoint for this resource, right? So it's going to be API/name/version/PDF documents. And then under short names is just the short name versions of the PDF document resource. So we could say kubectl get PDF, for example, so we don't have to do get PDFs. Line 9, if we move up, that's the scope, which is just saying that this resource has to live within a namespace. The other option that you have here is cluster, if you want to create cluster scoped resources. Then above that on line 8, we have the group name. So this, together with the resource version, is also the name that will be used in the REST API URL. So this is whatever we have on line 7, the group name, that's used on line 14 as a full API, REST API URL, right? Finally, on line 5, and I know we went like backwards up, we have to provide a name for this resource in the name field. And the way that this name is created is by taking the plural name, which is PDF documents, and then combining it with the group name. And group name is something that we define on line 8. So this is the first part of the resource. Again, this resource was fairly long, so I split it in 2 parts. The second part of the resource that would follow right after this one is where we are actually defining the list of versions or supported versions of the resource. Like note, every Kubernetes resource can have multiple versions, right? And those might be different. They might have different schema, different properties, different values, different requirements, etc., right? For our example, we only have a single version that's called V1. That's on line 2. And then under a schema, lines 5 and 6, and then everything until line 15. This is where we are defining the schema for our object. So Kubernetes is using the Swagger's Open API spec and to define how the objects can look like, right? So we're creating, for example, the document name, right? So we're creating an object that has this properties called document name and text with a specific types, which in our case is just a simple string. But this the Swagger's OpenAPI spec, Open API spec is fairly powerful. You can define required fields. You can also define specific patterns. If you say, oh, my name needs to conform to this specific format or this specific pattern, you can do that as well. And then if you try to create a resource that doesn't use a specified, that doesn't follow that format, the Kubernetes will throw an error and so on. Now, if we would go and deploy this custom resource definition, it will work perfectly, right? We will be able to create the instances of the PDF document. However, the thing that's missing is that controller, and this is what we'll do next. So let me switch to this guy here, and we'll go and create, and this is number 5, lab number 5. It's called CRDs. So the first thing that I'll do is I'll deploy this custom resource definition that I talked about on the slide. So you'll notice it has the name PdfDocuments. The group name is kubernetes.startkubernetes.com. This could be whatever you wanted it to be, right? Version v1, it has document name and text. And then we have the PDF document, documents, PDF, and PDFs. So let's do this one. So as soon as this is created, I can do kubectl get PDF document. I can list the resource right away. So Kubernetes created everything, right? So it created everything, the API endpoints, everything for us. Same thing I can do PDF, PDFs, of course, Kubernetes PDF documents. Like all those names, I can use that. And this also shows up if I list the resources, right? And I'm just going to grep for PDF. Let me do like this. So you'll see that there's, is it? I thought that was the, what was the, let's see, yeah. You'll notice there's a resource called PDF Documents. It has the short names, right? The kind. So it also lists, is listed there as well. Does an open source registry exist? How can a registry with the same name does not exist already? So if you're creating your own Kubernetes resource, I mean, I would just follow the same logic that you would do for like any public libraries. How did Java did things? They did like my company dot resource name or whatever. Just adopt some of the naming, right, that reflects and it's unique to you only. So if you need to create a resource that's called pod, don't call it a pod, right? Call it my company pod or something, right? But I don't know if there is a open source registry. There's a registry of all the, yeah, I don't think so. At least I don't know. But all the popular things that you would install, like Cert Manager or any other, like Cilium or whatever, all those things that we've installed or did, Ambassador, right? They have all their own custom resource definitions, right? So you could look at how they follow the naming patterns and all that. So also, let's look at the API endpoint that Kubernetes created as well. So let's do proxy. Just open the proxy here on port 8080. And then I think I can open it here. Yeah, perfect. So this is just the APIs. Can I do APIs? Yeah, if I do APIs endpoint, and then if I look at the PDF, what? It's not showing up? It should. Oh, it's the Kubernetes start Kubernetes, right? So the API was created for us, right? So we could look at this, and we could also do things like namespaces, default, PDF document, right? PDF documents. No? Right, V1. Oh, API. Oh, I'm missing the, it has to be the group name, of course, right? So it's Kubernetes start kubernetes.com/v1 namespaces default. So I'm just trying to say here that you can, yeah, there's nothing here, right? 0 items. What I'm trying to show here is that this PDF document resource that we've created is just, it's a full-fledged Kubernetes resource, just like anything else, right? Just like pods, just like deployments, right? Now, the only thing that's missing is there's no logic behind it. So let's create, actually, let me just close this one here. So we have one window, and let's create an instance of this PDF document, right? So we have this kind. Notice the API version here. So this is the group name / the version that we've defined, name of the resource, and then the specific things, the name and the text, right? So this created the PDF document. So if we list the PDFs, you'll notice that there's a item called my document. And then you can use the scribe as well, right? It'll show you the document. It's just like a normal Kubernetes resource. Okay, now this resource, once created, it doesn't really do anything, right? It's just some text. What we need to do is we need to create a controller that will do all those things that we that we talked about, right? It will watch for the PDF document resource, and once the resource is created, it'll create a job, and that job will create a pod with 2 init containers that will take that string from the PDF document resource and create a PDF document or PDF file out of it. So let me see if I have the Cube Builder installed. I do. Okay. So Cube Builder is just a tool that helps you build Kubernetes extensions pretty much. So there's a lot of like boilerplate code that goes into creating this. So it's just much easier to do it that way with a tool. So I created a separate folder PDF, and I'll initialize, excuse me. Know that this tool it'll generate Go code, but since there are SDKs for other languages, you could theoretically write this in any other language. I'm just using Go because it's by default in this tool. It makes it easier. So start Kubernetes.com. So we'll just initialize this, and this will just create all the basic files that will scaffold the project for us. I'll create the files, I'll create the structure, there's a lot of boilerplate code here. It goes into creating these controllers, right? So it doesn't make sense for you to like go and write everything from scratch if there are tools that do that for you. So this should be a couple of minutes. I think I should add like a Jeopardy song here or something while we're waiting. Maybe next time. Go here. Oh, I'm already here. Yeah, I already noticed that there's like a bunch of files that were created. Oh, okay, now it's done. Perfect. So let's list here. Yeah, it just created a project for us. And the next thing that we can do is we can create our API, right? So we'll do Cube Builder, create API. Our group name will be Kubernetes. Our version will be v1, and the kind will be PdfDocument. So it's asking us, do we want to create a resource, or do we want to create a CRD? Yes, we do. Do you want to create a controller for it? Yes, we do as well. So this will go in and it'll create everything that it needs to do. It'll create a controller. It'll create the a v1 folder, right, for our API version. There'll be a resource type in there. So once you create this project, you could, I mean, of course, you're probably not going to start with version v1, right? You'll start with alpha v1 or v1 alpha or whatever you want to call it. But what I'm trying to say is you could reuse the same project then and just add different versions, right? Okay, so let's open the editor and let me try to make this look better. I hope I can zoom in. So let's do this. I know it's kind of hard to read. It's very, and I haven't switched to dark mode on this one. Okay, so I can, yeah, this is like a poor man's zoom in, but anyway. I try to make this like this. I know it's not perfect, but that's the best I can do right now. All right, so this is the project structure. The important parts are here. API v1, this is where our PDF document type is created. So here you can see this is the PDF document spec. This is where we define how we want our PDF document resource to look like, right? So there's an example here. We don't need this foo. What we do want to do is we do want to add a document name, which will have a string name of document name here, and then we'll omit empty like this. And then we also need a text field. This is where we'll store the markdown text in the resource itself. Omit empty. There you go. So this is, we're just formalizing here how we want the resource to look like, right? It's nothing else. We're just formalizing it here. Now, once we have this, the next part is to actually go and implement the controller. And the way we do this is in the controllers folder. There's a file called PdfDocument underscore controller. And this is the file that actually, this is the logic that gets called, this reconcile method. This will get called when it's, I think it's, the comments are saying here, right, is it's part of the main Kubernetes reconciliation loop, which aims to move the current state of the cluster closer to the desired state, right? So this is where you can modify, we can modify the function to compare the state in the PdfDocument object against the actual cluster state, and then do any operations that we need to do to make the cluster state reflect those changes, right? So from this resource, we could actually get back from this request, right? So if I do, I hope this will work. So request, we can get the namespace, right? And the namespace and the name of the object that was created, right? So what we can do here is we can, let's create a PdfDocument and then Kubernetes PdfDocument instance. And then we can use this reconciler object to actually get an object, right, from the cluster, right? So this is going to get called whenever there's a change or whenever the PdfDocument gets created or changed, right? So what we want to do is we want to use the namespace name. So this is the full name of the resource, right? We want to get that resource into the PdfDocument here, right? And then we want to say if, and I know this is like Go specific, but we're just checking for errors here. And then over here, we actually need a log, right? So we can log error and say something went wrong. Something went wrong. Of course, you'd make this better, not like this. And then we also need to return, right? And what we're returning is an empty result because we actually haven't created anything. And then an error saying that we could not find this specific PDF resource that you told us that you've created, right? Okay, so then the next thing over here, what we want to do is we actually want to create the job with the init containers that will take the contents of the PdfDocument resource and we'll say create a markdown file and store it in a shared volume. And then 2, so this will be init container 1, and then 2 init container 2. This one will read the markdown file from shared volume and run pandoc to convert it to PDF, right? And then 3, this will be our main container, right? Main container sleep, right? It'll just sleep here just so we can inspect the results. So let's create a separate function here, and I'll copy paste a bunch of code here because I don't think it makes sense for you to watch me type all this code in. If I can select everything properly here. Oh, come on. So close. Let's see what this does. Okay, can I remove this? And I can remove this. And let me just fix up the import statements because I'm using a couple of things here that are not defined. So I'll go up here. I think I need to add FMT as well. Move this one like this. And then we need to add base 64Ys. And oh, there it is. Perfect. Add this import. Should be fine. Now everything should be fine now. Yes. Okay, let's look through the code. So this is, actually, let me go back here. So over here, once we have the reference to that PDF document, right? Once we read it and there is no error, what we'll do is we'll create a job spec, right? So we'll create a job. So this is that function that I just pasted in. We'll pass in the PDF document, and it'll say if there's an error, right? We'll just say return control result empty, and client ignore not found, or whatever the correct error here would be, plus the logs here, right? Error. And we'll say failed to create a job spec, right? And then down here, we'll actually go and create this job, right? So we'll create, well, not this one, we'll do create, right? And then we'll say context and pass in the job spec object. And just check for errors again. If error is not empty, if we got an error, log error, unable. I don't know why it does double parentheses. Unable to create the job, right? And then over here, we'll just return an empty result. We don't have to return anything here because we're returning here, so it doesn't really matter. Okay, so let's go into this create job function that we wrote. So there's a lot of stuff here, but it's just because this is just a job specification. It's a YAML file, right? If this was more like refactored and everything, I would probably have a YAML file somewhere in like as a file itself, and then just replace the values in, read the file and replace it. But I want it to be very explicit here. So what I'm creating here is I'm creating a job, setting the name and namespace. So the name of the job will be whatever the PDF document's name is, and we'll just append job to it. You can already see an issue here, right? Namespace will be in the same namespace as the PDF document is in. And then this is where we're defining the our pod spec, right? So this is what our job will create, right? We will have first, we'll have 2 init containers, right? The first one will be called store to MD, and this one will store the contents of the text field from the PDF document into a markdown file. So what I'm doing up here, line 85, is I'm actually reading the value of that text and then base 64 encoding it, so it makes it easier to echo it into a file. And then in this first init container, just using this as an Alpine image, I'm just calling out to echo that string, which is this one. I can't move because I'm zoomed in. So there's base 64 text here, right? That gets replaced. So I'm echoing the content of that base 64 encoded string into /data/text.md file, right? And this data path comes from a volume we mounted down here, which is just an empty dir volume. There's nothing in there, right? So this will be the volume that will be shared between the containers. So once this init container is done, we have a file called text.md in the data folder. Then the next init container runs, which is called convert. And this one is using the pandoc image. So pandoc is a tool for converting to different document formats, to and from. And it's just saying, convert this text.md to this string, and this string, let me zoom out, is the document name, right? So this is the document name that we defined in the PDF document resource, right? So it's saying, take this data, text.md, convert it to the PDF document under the same data folder, right? So once the second container completes, we end up with a .pdf file name in the data folder, right? So we basically converted the markdown to PDF. Finally, we have our main application container, and this one doesn't do anything. It just sleeps, and it mounts that same volume just so we can go in and see what was happening there, right? So this is pretty much, it's stupidly simple logic here. Not a lot of error checking. There's a lot of issues here. You could do this differently and better, but just to show you an example of how you could go and write your own controller, a very simple controller, reconciler method, right? How to do it. Of course, there's not all cases here, right? That are covered, like what happens if I update the PDF document resource, right? This is not going to work, right? It'll try to create a job with the same name, right? It's not going to work. It'll fail. So if you're writing a container for reals, right, you would, or controller, right, for real, you would probably have to handle all those cases, right? Okay, so let me zoom out here, and then I'm back to 100%. We'll go to the code. So one thing that I need to do is I need to get those packages that I'm using, and this is, again, Go specific thing. Don't worry about it if you're not doing Go. And then let me also, I'll delete this my document, and we'll create it, delete PDF my document, okay? And now we can actually run the controller against the current cluster that I'm using, right? There's a whole set of things that you have to do if you want to deploy this and share this with someone else. I'm not going to go into that because it's that specific to like the tooling that you're using. And I think that this cube builder does build stuff for you, right? So it creates like deployments for you, RBAC rules, right? So you could look into this and see how to actually create a controller that you can deploy, right? So I'm just going to do make run, and let's see once this starts. So this will do all the building. It will build the controller, and then it will actually deploy and run the controller against the Kubernetes cluster that I have running. So this could take a couple of minutes. Not sure how long this usually takes. Shouldn't be too long. Hopefully soon. Okay, and now it's running. So let's split the windows here. So we have the controller running on the top screen. And now what we can do is now we can create that PdfDocument resource, the same one that I was creating earlier, right? Same thing, but this time we'll actually get some logic behind it, right? So let's look at the PDF. So we have this document, and now let's look at the jobs. So you'll notice there's the my document dash job that got created because we created this resource, right? Also, I still have the, let me delete the goodbye pod and no egress pod because they don't make any, oh, it has to be pod. Let me move this higher up, clear, and pods. So you'll notice it's still getting initialized, and this is because I have, it's a clean cluster. It's trying to pull down all the images. I think we can look at my document job for this one. Okay, so it's still being initialized. We can describe perhaps, right? So it's still running, right? It's pulling the image. So store to MD is done running. Now it's pulling the PdfDoc image. I think that image might be bigger or something. That's why it's taking so long. But as soon as this is done, we'll be able to look at the, we'll be able to go into the container, into the pod, and actually look at the PdfDocument, the results, right? So let's see if we can do, I don't think there'll be any, yeah, there's nothing, we're not logging anything out. There you go. Okay, so it started the container convert, right, just a second ago. Oh, wow, it took like 1.5 minutes to download this PdfDoc image. I wonder how big this image is. Anyone cares to guess? PdfDoc, let's see. Oh, wow, it's 1.3 gigabytes. I guess that's why it's so slow. All right. Okay, but I think, yeah, now the pod is running, right, which means that this conversion then probably completed. So let's look at my document job for, let's do bin bash. Oh, sh, sorry. There we go, right? So now if we go under data, you'll notice that we have the mytext.pdf, and then we do have text.md. This is the actual text that we had in that resource. So let's, oh, if I can type. So let's copy the file from within that container. So I'll do kubectl cp. I think this, I haven't shown this command before. So cp allows you to copy stuff from within the container to your local machine, or the other way around, the PDF. And then I think I have to do the full name here. I'm not sure. Let's do this. Oh, mytext.pdf. Okay, do I have it? Yeah, I have mytext.pdf here, and then there's a way to download files. And we'll do home PDF, mytext.pdf. Just download the file so I can open it, save it, open it, and boom, there you go. This is the title, and here's the bold text, and this is the same, the contents that we had in our PDF document resource. Now you can imagine that this could, like, instead of just leaving the file there, you could have that last container. What it could do is it could maybe just upload that PDF document somewhere, right, for you. Or, since we talked about persistent volumes, right, you could use like you could hook the volume up to like your Google storage account or whatever, and then just store all the PDFs there, right? So whenever someone creates this PDF resource, right, whatever the use case is, right, you could have the files be converted automatically for you into a storage account, right? Or you could send it to an API, or you could email it. I mean, there's countless different scenarios and options that you have. All right, so this was the last thing that that I had. We're not going to take a break for you to like go through this. Yeah, you can go through it on your own. So for next time, I didn't really have anything planned for next time. I think there's one thing that we could do is the operators, which are very similar to what we did with the controllers here, right? They just watch for resources being changed or updated. I could talk about that, or I would prefer, if you have any questions or any areas or anything that you want me to cover, leave a comment, join the Discord, ask questions there, and then we can hop on and I can do another live stream on specific topics. The other option is just going back through same contents that I already did, but go through them deeper, right? Because this was, I mean, it was 4 weeks, 3 hours each week, right? So it was a lot. It's a lot of content, right? But it's still just barely like scratching the surface. We could easily spend like hours on one specific topic itself. Difference between KubeBuilder operator SDK. Honestly, like I had this example. I think I've done this example a year ago, right? So I haven't. I don't know why. I don't remember the exact reason why I went with KubeBuilder versus the operator SDK. I can't remember what the reason was. But if there's another one, like I don't know which one is used more or less. I don't know. Let's see, KubeBuilder. If we look at the GitHub, right? 4,000. They're pretty close. I don't know. So KubeBuilder has like 4,000 stars. I don't know if that's saying anything, right? And then Operator SDK has 4.8. So maybe Operator SDK is better, but or at least more people click the stars there. But yeah, definitely I could look into maybe let's do Operator SDK next time. I don't know if next time will be I don't know if next time will be next week necessarily, but in the coming weeks, I could look into it. It would be interesting to look into the Operator SDK more and do something that's more like real world, not just a PDF document, right? Okay, awesome. Thank you very much for joining, and then I'll watch for the next session when it'll come up, maybe in the next couple of weeks. We'll talk then. Thank you.